Static batches make short requests wait for the slowest sequence. vLLM continuous batching replaces finished slots immediately, increasing concurrent throughput without delaying every user. After this, you'll understand how to assemble a pipeline that compares batching styles and reports throughput, queue time, and request latency. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. When you fire lots of small chat requests at a model, a single long reply can block everyone else. Teams hit this when lookups and long generations share the same path, and naive client-side batching only makes the waits worse. vLLM gives you an OpenAI-compatible endpoint with a scheduler that can pack and repack work more fluidly. Short jobs finish faster, and the GPU stays busier. At a basic level, continuous batching is simple. Stop sending traffic in fixed waves. Make every request eligible, and let the server fill slots as they free up. That trims idle time, usually raises tokens per second, and cuts how long requests sit in queue. We'll build a small benchmark that checks the server, sends one mixed request to validate timing, runs a static grouped baseline, runs an all-at-once concurrent run, and finally pulls server metrics to separate queue time from generation latency. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we'll hit the vLLM endpoint and confirm which model it's serving before we start timing anything. This snippet makes the client confirm which model the vLLM server is actually serving, so we fail fast if the endpoint, API key, or model registry is wrong. The OpenAI client is pointed at localhost, and client.models.list asks vLLM what it is actually serving instead of hard-coding a model name. Keeping model in a shared variable also prevents later benchmark calls from drifting to a different deployment. The visible served model confirms the Python process can reach the same vLLM server used for the rest of the run. Next, we build a mixed request and run a single smoke call to make sure the workload shape looks right. This example shows one mixed request set and a single vLLM chat.completions.create smoke call to validate timing and workload shape. Mixed max tokens values matter because static batches often wait on the longest generation, even when short requests finish first. Jobs keeps the name, prompt, and output cap together, while run job records client-observed latency and returns completion tokens from rest.usage. Temperature equals 0 reduces variability, so latency comparisons are easier to read. The visible smoke request, seconds, and tokens demonstrate that the workload shape and timing wrapper behave as expected before we add concurrency. With a validated workload, we build a static client-side batching baseline to capture the pain of fixed group fences. This code runs jobs in fixed client-side groups, so the next wave waits until every request in the current group returns. That mirrors static batching pain. ThreadPoolExecutor gives each group 2 simultaneous calls, but the for loop creates the artificial boundary that continuous batching is meant to avoid. Static wall captures end-to-end time for the whole baseline, and static mean summarizes per request latency from run job. The visible static wall and mean latency give you the baseline to compare against a more fluid submission pattern. Now remove that artificial fence and make every job eligible at once so the server can fill freed slots continuously. This snippet submits the whole workload at once, so vLLM can schedule requests continuously, rather than waiting for client-imposed group boundaries. Instead of holding later requests behind a fixed fence, ThreadPoolExecutor makes all jobs eligible for service immediately. vLLM still decides how to batch internally, but the client stops creating artificial pauses. Speedup compares static wall from the baseline with live wall from the concurrent run, while live mean keeps the per request view in frame. The visible continuous mean and speedup show whether removing the client-side barrier helped this workload. Finally, we connect client-observed behavior with server-side queue metrics so we can separate waiting from actual generation. This example fetches vLLM's metrics endpoint and computes the cumulative average scheduler queue time to separate queue waiting from generation work. Client latency tells you what users felt, but the Prometheus histogram helps split waiting time from compute time. vLLM.request fetches the metrics text. Metrics selects vLLM request queue time seconds, and the code divides the histogram sum by count to get QMS. Talk per sec uses the completion tokens returned by live and the continuous runs live wall for a compact capacity signal. The visible server QMS and tokens per second connect incident-style queue pressure with useful generated throughput. If you map this toy run to a real system, measure the same signals at your API gateway and at the inference host. Emit client-side latencies, per request completion tokens, and the server histogram under steady load, so you can trace spikes back to queue pressure or true generation cost. Continuous batching hands free GPU slots to waiting requests instead of pausing for a full client group. Use it when you mix short and long generations, and you care about per request latency and overall token throughput. One thing to watch: server-side scheduling details and model-specific throughput can change how much benefit you see. A practical next step is to vary the mix of max tokens and measure tokens per second and server QMS as you shift the short to long ratio. That single parameter will reveal how batching shapes capacity versus latency for your actual traffic. If concise, practical AI engineering helps, subscribe and watch the AI engineering videos.